Okay, this is what we have been doing. We're working in chapter number 3. We talk about the C in object. We know that in order to work the C in, just like the C out, we have to use the pound include preprocessor directive. We work with some mathematical expressions. We learn about the hierarchy of operations. First, everything that is in parentheses is going to be solved. Then we have the multiplication and division. Then we have addition and subtraction. And everything is going to be from left to right. Right? That's the way that it's going to be executed. C++ does not support raising a number to a power, so we use the POW function. In order to use the POW function, we have to use the pound include CMath. Okay, the CMath. It's again another preprocessor directive that is going to be able to help us use this function. So today we're going to start with the section 3, which is data type conversion. We're going to talk about overflow and underflow and name constants. So we're going to jump there. Any questions on what we have been working with? Okay. First of all, if you remember in the project that we solved last time, it was changing the temperature from Fahrenheit to Celsius or from Celsius to Fahrenheit. Remember that? And we had one division. We had 2 INTs, 9/5. And every time that we were doing this division, because we were working with INTs, it was giving us an INT answer. So we found that we had an error there. We had a logic error. So we had to convert one of them to an absolute number, right? Well, not a real number, right? Absolute position number. So we had to put 5.0 or 9.0. One of them had to be converted. So, and we know that this happened because when the 2 INTs are used in an operation, the result is going to be an INT. When we have an INT and a floating point number, then the floating point number overtakes, right? It's going to have a higher data type, we call it. So the answer was going to be a floating point number. So here it's Y. Here we have the highest data types. First, we have the long double. The more space it uses in memory, the more hierarchy it's going to have. Okay, it will overwrite everything else. So if I have an operation between an INT and a long double, the result is going to be a long double. Then after the long double, we have the double. Then we have the float, then the unsigned long, then the long, then the unsigned INT, and then the INT. Of course, we can go down and we can put the short here underneath the INT. So it's going to be ranked by the largest number they can hold, which is equal to the space in memory that is going to be occupied. So if I have, again, an operation that is going to be involving an INT and a float, the result is going to be a float. Okay, because this one is going to be overriding the INT. So we have to remember that. And it's very easy to remember. We know that when we have whole numbers, we're going to be using the smallest is going to be the short, then the INT, and then the long. If we're working with floating point numbers, it's going to be the float, the double, and then the long double. So of the 6 that we just mentioned, the highest is always going to be the long double, and then we go down all the way to the short. Any questions on this? This is just something that we need to remember. This is the same thing. So what if I need to change? What if I need to change? We did it because we were working with the 9 and the 5. They were constants, and we were not going to use them anywhere else in our program, and we just needed to change that. So it was easy just to change the 9 to a 9.0 or the 5 to a 5.0. But sometimes we need to make a casting, we call it, a change of type, but using code. Okay, using code, and in this case it's going to be a function that we're going to be using, and the function is called static cast. This is the name of the function. So static cast is going to help us change, like the 9 from, this is an INT, it changes to a 9.0, which is now going to be a double. And then we can use it as a double, right? We did it just by changing, again, the code that we had, right? Now, there is a method that we can use that is going to involve code. And what is that method? It's going to be a function. And the function is going to be static underscore cast. In the angle brackets, we're going to write the new data type. Like in this case, I want to change the 9 to a double. So I will write static cast, open the angle brackets, and then put in here the double. And then in parentheses, what I want to change. What I want to change. So in parentheses, I will have my 9. So in my program, when I was doing the operation, it was something like Fahrenheit, it's assigned the value of 9 divided by 5, right? This is what we had. In order for this to work, we had to change it 9 divided by 5.0, right? Another method will be 9 divided by static cast, underscore cast, open the angle brackets, put double here, close the double brackets, and then in parentheses put the 5 and close it. We don't need to put the 5.0 because that's what it's going to be changed to, right? We had to put the original value, which is 5.0. In the example that they are giving us here is they are using the static cast for a cout. We were using it for a formula, and they are using it now for a cout. That means we can use it either way, right? We can use it in an assignment operator, we can use it in a cout. So here we have static cast, it's an INT, or I want to change it to an INT, and right now it's a double. So this one, the 4.2, is going to display as a 4 because the 0.2 is going to be truncated. So here's another example. We have character, and this is a variable that is called CH. So in main memory, we have CH, and it has the C inside. Then we're going to display cout, the CH, which is going to be the C, right? And then the message is stored as, so C is stored as, and then we have static cast. Change it to an INT. What do I change to an INT? The C. So let's suppose that the C, when we change this C to a number, this is going to be a 64. So this is what is going to display. C is stored as 64. Again, here they are using it in an assignment operator. Let's suppose that area we have 1005. That's what we have in area. Area, it's assigned this value. Okay, so then we have this line. We have gallons is assigned the value of static cast INT. Okay, so change it to an INT, whatever it's the result of this operation. So area is 1005. How many times will 500 go into it? 2 times. The remainder is going to be a 5. So 2.005 is going to be change to an INT, so whatever we have as the decimal portion of that number is going to be truncated, and we have now a 2 because we're changing it to an INT. So as we can see, we can use parentheses in the static cast, we can use parentheses and just put a value. It can be, like in this examples, it was just a number, right? Here they are using now a variable. Here they are using an expression. We have another example here. Average is going to be assigned the static cast to a double, so change it to a double, whatever you have here. Sum divided by count. This is similar to the example that I gave you about changing the 9 or the 5. So these are just different examples of how we can change values. We can change values that are going to be displayed in a cout. We can change values that are going to be in a formula. We can change values independently using the static cast. This is just how it was done in C. We're not going to go into that. C style. The next topic is overflow and underflow. Overflow is going to occur when we assign a value that is too large. Too large. So if I have, I suppose that I have an INT. An INT is going to be 4 bytes. 1, 2, 3, 4. And I have the highest value. Okay? It's an unsigned INT, which means so we are using all of the bits. So we have, this one has 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, and they are all on. 1, 2, 3, 4, 5, 6, 7, 8, all on. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So every single bit in my INT is on. If I try to add one more bit, plus one more bit, and then all of them are going to be zeros, all zeros, this is going to create an overflow. Why? Because I'm already at my highest number that I can keep in this 4 bytes. So I try to put a point, the 1 byte more, which is 1 more, and it's going to just overflow it because it's going to say, hey, I cannot store more than what I can hold. So this is going to cause an overflow. The same thing will be if it's too small. If it's too small, let's suppose that I have all of my bits are off. They are all off on my 4, 1, 2, 3, 4. And I try to subtract a -1. This is going to give me a negative number, right? 0 minus 1 gives us a -1. But this one, it's a INT without a sign. Can I put it in there? No. This is an INT. It's an unsigned INT, which means it cannot hold negative numbers. I cannot put any signed numbers in there. So what will happen is it's going to create an underflow. If I limit this, if I say this is an unsigned INT, which means no negative numbers, and I want to put a -1 in there, then it's going to create an underflow. Why do I want to create a -1 in it? Because I've had the smallest value, which is the 0, and I try to subtract a -1 from it. So the result is going to give me a -1, which I cannot hold because I can only hold positive numbers. So this is going to cause an error. Either way, if it's too the value is too large, it's going to cause an overflow value, or if it's too small, it's going to cause an underflow value. Here they're just giving us the example. First, they created a short and initialized to the largest value that it can hold. What is the largest value that it can hold? A short int is going to be 32,767. So here it is. And we display that. And then we try to add 1 to the 32,767. What happens here? I cannot hold a 32,768. So when I display this num, this is going to display a wrong value. This is not correct. So this error is said, we call it an overflow. This cannot be. So are we going to be able to notice that error when we're doing the code? No. It's going to be a logic error. So we have to be very aware of that. So how do we handle this overflow? Different systems handle it. Sometimes they give us a warning or an error message or display a dialog box. In our system, it will not do it. It will not stop the program. So what it will happen is it will just continue execution with the incorrect value. So it's going to give us the logic error, just like what happens when we were changing Celsius to Fahrenheit, that we were not getting the correct value. So we have to be aware of that. You will find more examples of this in your book. Okay. Name constants is the next section. Name constants. We know that we have been using constants like the 9 and the 5 in the last program. So any number that we use is a constant. It's a constant. This is a numeric constant. When I use high in double quotes, this is going to be a string constant. If I use just one letter with single quotes, this is going to be a character constant. So now we're going to be introduced to naming these constants. We were not naming the constants. When will it be a good time to name constants? If I'm going to be using that constant throughout the program, and if it's something that is going to be changed often. Let me give you an example. Let's suppose that we are going to create a program that is going to be calculating the sales tax for the city of Brownsville. So we have in the program, we use the sales tax, which is $8.75, right? So we put 0.0875. Okay. And we're going to use it like 10 times in the program. So every time that I use it, I'm going to put 0.0875, 0.0875 times whatever, 0.0875 times whatever, and so on. But we know that so many years passes, and then they change the tax rate. So instead of going to the program and change 0.0875 to 0.09, maybe they increase it this year, 10 times, it will be much easier if I just have it on the very top of my program. Where I define my variables, I can define also this constant. And I'm going to write, hey, this is going to be a constant, like this one. It's going to be a double, it's going to be tax rate, and it's going to be 0.0875. And every time that I use it, those 10 times that I was using 0.0875, instead of putting 0.0875, I'm going to use this name, tax underscore rate. So when the change comes, and we move from 0.0875 to 0.09, I only need to change it once at the top of my program. And I know that when I change it once on the top of my program, every occurrence is going to take that change. So instead of having 0.0875, I'm going to have 0.09. So let's see here. They're also called constant constant variables. Okay, this name constant. And we call them variables because, again, we are separating an area in main memory. But we cannot vary that value. Okay, we cannot change that value like we do it with true variables. Constants means they remain unchanged throughout the execution of the program. So they are variables whose content cannot be changed during the program execution. They are used for representing constant values with descriptive names. So we're going to use a descriptive name. Tax rate, number of states. One of the recommendations that they do for us programmers is that we use uppercase to name them so that we can separate the variables from the constants. The variables, we use lowercase letters. When we're using the camel format, we use the first letter of the second word is capitalized, right? Second, third, and so on. So this one, they are recommending that we do all caps, okay, for naming the constants, which is what we're going to be doing. What are the benefits of the constants? Make the program code more readable by documenting the purpose of the constant. So instead of just putting 0875, I'm going to be calling it something, Brownsville sales tax. So when another programmer checks our program for updates or anything, it will be much easier to see, okay, the 0.875, what was it? Oh, is the tax rate for this location, versus it already has the name and it's going to be much easier. And simplifies program maintenance. What I told you, if I need to make a change, instead of changing it 10 times, because those are the times that it occurs in my program, I only change it once. So it's going to simplify the program maintenance. Where are we going to be coding this? We're going to be coding it where we define our variables, which is at the very top. In C, the C style, which I'm just going to name it, but we're not going to use it. They work with the includes, the preprocessor. So they use a pound define, just like a pound include. Okay, they use a pound define and then they name it. In C++, we don't use this anymore. So this is going to be interpreted by a preprocessor rather than the compiler. We are going to stick to using the C++ style, not the C style. Okay, I have the book open already, so you don't have to open yours. And here on page 91, it's our data type conversion. It starts this section, what we cover right now. And we also have the named. And I want to go to the checkpoint. I'm going to recommend that you use the checkpoint to review. So we're going to do this first one on page 97. Okay, just so that you can keep that. We're going to solve this as a class. It's checkpoint 314. So I'm just going to put it here to the side, my word, so that we can do this. Don't worry if you don't have it open. So let's try this. Assume the following variable definitions. We have an int, A is assigned the value of 5, and then B is assigned the value of 12. So we have two variables here. Then we have double X is assigned the value of 3.4, and Z is assigned the value of 9.2. What are the values of the following expression? What do we have in A? B divided by A. What will be the answer? Why 2? There are 2 INTs. So the operation is going to be 12 divided by 5. 5 goes into 12 2 times. We have a remainder, but do we use a remainder for the result? No, it's truncated, right? Yes, everybody? Okay, next one. X times A. X times A is going to be X is what type? It's a double. And then A is an INT. So it's 3.4 times 5, right? That is the operation. What are we going to get as a result? I have 17, 32.
No, I did the 3.4 times 9.
This is the one that I was looking for. So what was the result? 17? Are you sure? Would 17? 17 by itself?
Or 17.0.
17.0. Thank you. Why 17.0? Because the X is double. So we're going, remember that is going to take over the smallest data type. So double has the highest, a higher hierarchy than the INT. So the result is going to be a double. Okay, now let's see. Letter C. Static cast, double, open parenthesis, B divided by A, close parenthesis. The answer is going to be what? 2.4. Why 2.4? Because it changes to a double. It changes everything to a double. Okay, the next one. $2.4. Let's see, let's jump to H. Letter H. Static cast X, it's an INT. Static cast Z is an INT. It doesn't round. This one's, they don't round. When we move to another data type, it doesn't round. 27? It's letter H. I jump all the way to letter H.
Yeah, but is it converted before?
It's going to convert it. The X is going to be converted. The Z is going to be converted. And then the multiplication is going to take place.
Okay, so it's 3 times 9.
Yes, 3 times 9 is going to be at 27, and it's going to be an INT. Let's go back to this one, because I didn't see it correctly. Letter C. Static cast, the double, the angle brackets, and then the parentheses. B divided by A. What happens here when we have parentheses? It will do that first. So we have B divided by A. It's going to be, the answer is going to be 2, right? So when we change it to a double, the answer is going to be a 2.0, okay? A 2.0. The letter D, this is going to give us a 2.4. A 2.4 because the B is going to be converted first to a double. So the B is going to be 12.0, and then it's going to be divided by a 5, 12 divided by a 5 is going to be 2.4, okay, because the double takes over. So you have here the checkpoints, 14, 15, I think there's another one that you can use, and I'm going to jump to the overflow and underflow section for the checkpoints. No, in the cast, I don't think they have here checkpoints for this section. Let's see. Here, checkpoint. Write statement using the constant qualifier to create name constants for the following literal values. So this is going to be, this is a constant value. This is the description. This is known as the E, which is the mathematical E. This is going to be number of minutes in the year. This is going to be the gravitational acceleration constant. This is the same, but meters per second. And this is the value numbers of meters in a mile. So if I'm going to be creating a name constant for this one, just a name constant. Okay, let's see how do we create name constants. We use the keyword CONST, then the data type, then the name, the assignment operator, and then the value. So we use CONST, then the data type. What data type do we need for 2.71828? Double. Then a name. What name do you want to use? They recommend that we use all caps, right? So let's use all caps. I'm going to put it here. And then the assignment operator, and then the value, 2.71828. And I close the semicolon. Where am I going to have this? Again, this is going to be where I define my variables. Okay? At the very top of my program. At the beginning of my program. Is there a way that I can increase? There we go. So you can see it better, right? Because you're having problems reading it. Okay. So we have this first one. The next one, number of minutes in a year. So we use the same thing. We start with CONST. I want to make sure that this is not capitalized. Okay. Then what type do we need? The number of minutes in a year. What type do I need? It's 5.256e to the 5th power. A long double, just to make sure that it's going to fit in there, right? And then a name. What name do we use? Minutes in a year. Then the assignment operator is assigned the value of 5.26E5. Well, C++ recognize what E means? Yes, yes. When we were talking about constants in chapter 2, we talk about decimals. That's where we were introduced to whole numbers and to floating point numbers. Exponents, exponential format, which is this one. Octal, remember that I mentioned octal, and hexadecimal. Those are the numbers that C++ is going to recognize, those formats. So this will be a valid definition. Then we have 32.2, which is the gravitational acceleration constants in feet per second. So again, we start with CONST. Then it's going to, what data type do I need? We can put a double. And then we're going to call it gravitational or ACC, acceleration feet per second. It's assigned the value of 32.2. Semicolon, and we're done. This is a double. And then again, the next one, CONST. It's a constant. It's a 9.8. What data type do I use?
Double.
We can use double, but let's change it a little. What else can I use? Float. Float. ACC underscore meter per second. It's assigned the value of 9.8, semicolon. And then the last one is a constant number of meters in a mile. CONST. What do I use? What data type? INT, and it's going to be meters in a mile. And it's assigned, so I use the assignment operator and then 1609 semicolon. Okay, if I need to use the 5.26, I'm missing 1 5 over here, right? 1 5. If I need to use this value, am I going to use it? No, I'm going to be naming it, right? I'm going to be using this name, minutes in a year. If I need to use the 1609 number, I'm not going to be typing 1609. I'm going to be using the name meters in a mile. Again, and we need to remember the advantages of using that. For the maintenance, maintaining the program, it facilitates our work very, very much. And it's a good way to document everything that we have. Questions? Okay. Now we're going to go back to our presentation, but I just wanted to show you where we have the checkpoints in our e-text so that you can go back and review all this. Okay, not only read that section, but also do some of the checkpoints that we have there. You have the checkpoint answers in one of the indexes. The last index, I think. You will find everything there. I cannot get my menu. Oh, here it is. I found There we go. Let me show it to you so you know where to find it. Answer to checkpoints in Appendix C. So we have it here. Okay, any questions on name constants, overflow, underflow? Okay, so we're going to continue with operators, arithmetic operators. And now we're going to talk about the assignment operator. We know that the assignment operator is what we call the equal sign, right? Anywhere else except in C++, we always call it the assignment operator. It's going to be the way that this one works. Whatever I have to the right of the equal sign is going to be moved to the left of the equal sign, right? So this part is done first, and then this part is done second, always. Okay. That is the simple assignment operator. We have the combine now, the combined assignment. The combined assignment is going to have something else. But before we go into that, let's see. So if I have this line right here, this is a valid line. And what happens is it's going to work again from right to left all the time. So this 5 is going to be the first thing that the computer is going to check, or the compiler is going to be working with. And it's going to say, okay, the 5, I have to move it, because here it is, to the variable z. So z is going to have a number 5. This happens. Then it's going to find another assignment operator. So it's going to say, okay, now this z, I'm going to move it to this variable, y. So now this y, I'm going to move it to this variable, which is x. So at the end, all of them are going to have the same value. Why? Because the way that it works, going from right, solving whatever we have there, and then moving it to the variable that we have on the left-hand side. There can only be one variable on the left-hand side. So I can have z plus 1 here. That will be incorrect. The combined assignment operator. Now we're going to have two operators. We can have a plus and an equals, the assignment operator, the minus and the assignment operator, the asterisk and the assignment, the division and the assignment, the modulus and the assignment. So what this is going to do is going to do this operator first, and then it's going to do this. This operator first, and then it's going to do the assignment. And it's going to do all of them. First, and then the assignment. First, and then the assignment. So it's going to apply an arithmetic operation to a variable, and it's going to assign the result as the new value. So if I have sum plus equals 1, and sum is a variable that has a 10, what it's going to do is it's going to apply the operations. It's going to say sum plus 1, as if this one did not exist. So it's going to say sum plus 1, it's 11. And then what do I do? This is operation number 1. And then what do I do? Assigns. So the 11 that is in the arithmetic unit is going to be brought, and it's going to be placed in sum. And sum had a 10, now it has an 11. Another name for combined assignment operators is compound operators, or arithmetic assigned operators. So we have here the first example, x plus assignment 5. What is it going to do first? It's going to add x plus 5, and then it's going to move it to the variable x. 1 and 2. First, the arithmetic operator is going to be solved, and then it's going to assign it. In this case, x minus assignment 5. So it's going to do again x minus 5, and then the result is going to move it to x. 1 and 2. So the right-hand side is evaluated before the combined assignment operator is done. If we have a larger expression, like in this case, a plus b is going to be solved first. Whatever result we have from here is going to be multiplied. This is going to be second. And then the result of everything is going to be moved to x. We always follow the rules. Okay? Questions?